Hey there guys, welcome to Unit 1B Notes G. Today we're going to review and go a little bit more into depth. We're looking at gas laws. So let's first start off with Avogadros Law. Avogadros Law essentially says that equal volumes of any gas must have an equal number of particles. It doesn't actually put any numbers to that, as although we did eventually get into Avogadros number and such, the law itself really just focuses on an equivalency between two gases. So say I have two containers full of two different kinds of gases. One where the particles are really big and one where the particles are really small. They would still take up the same total volume because gases are compressible. They can vary their spacing and still have the same net total volume. So if you have the same amount of gas, it will take up the same volume regardless of its identity. Avogadros Law. Now let's put a little bit of number to it. We have a standard temperature and pressure, which we learned in honors was 1 atmosphere and 0 Kelvin. Or I'm sorry, 0 degrees Celsius, so 273 Kelvin. Well, that was actually not entirely truthful. As it turns out, 1 mole of gas should not be 22.4 liters per mole, but actually 22.7 liters per mole. And that's because the definition for standard pressure actually changed in 1982. Instead of using 1 atmosphere as the basis for standard pressure, it actually became 100 kilopascals, which is close, but not exactly equal to 1 atmosphere. 1 atmosphere is actually equal to 101.3 kilopascals. So if we adjust our standard pressure to be a little lower, the gas will take up a little bit more space, precisely 22.7 liters at the actual standard temperature and pressure. Now, if you go to college in the United States, odds are they're still going to be using 22.4 liters and 1 ATM as your standard temperature and pressure. But it really did, industry standard really did change in 1982, and this really should be the numbers that are being used, and this is what IB is going to use. A pressure of 100 kilopascals and a standard volume of 22.4 liters, assuming that we have a gas at standard temperature and pressure. So I know that can be a little bit to wrap your head around. I understand if you need to pause and walk away for a minute, but we're moving on. So now let's look at a problem just with this idea that equal volumes would be consistent for an equal amount of gas. Keep in mind that amount is typically measured in moles. So we have 40 cubic centimeters of carbon monoxide. I'm going to go ahead and note that on my equation here. Carbon monoxide, 40 cubic centimeters. Then it also says it reacts with 40 cubic centimeters of oxygen gas. So my oxygen is also present initially at 40 cubic centimeters. So then the question is, what volume do we think carbon dioxide would occupy as an end result after this reaction occurs? So what would we do? Would we add the volumes together to get an increase in volume? Would we find the difference? I guess meaning that there's no volume. That doesn't really make sense. Think about Avogadros Law. Avogadros Law simply says that equal amounts of gas must have equal volumes, which means that if there's 2 moles of carbon monoxide taking up 40 cubic centimeters, then 2 moles of carbon dioxide would also take up 40, here let's do in purple, our answer, 40 cubic centimeters. So does that require all 40 cubic centimeters of oxygen to be used? What would be the volume of oxygen after this reaction? Does all 40 cubic centimeters of carbon monoxide react with all 40 cubic centimeters of oxygen? Well, no, because the mole ratio here is 2 to 1, meaning I use twice as much carbon monoxide as I do oxygen. Or in other terms, I use half as much oxygen as I do carbon monoxide. So if I'm using 40 cubic centimeters of carbon monoxide, I'm only using 20 cubic centimeters of oxygen. And then if I wanted to, I could find the difference. Well, if I had 40 and I used 20, then I also have 20 cubic centimeters of oxygen in excess. So the reaction uses 40 cubic centimeters of carbon monoxide and 20 cubic centimeters of oxygen. It produces 20 cubic centimeters of CO2 with 20 cubic centimeters of O2 left over or in excess. And this can all be determined just by looking at the mole ratios and considering Avogadros Law, which says equal amounts of gas or moles of gas should have equal volumes. So if you're given the volume for one, you can determine the volume from the other, just from our mole ratio. In this one, we produced 40 cubic centimeters of CO2. Twice as much CO2 being used than O2 will leave a remainder of 20 cubic centimeters of oxygen as well. So that's another way to approach problems using Avogadros Law. Now there are a couple more things that are a little bit different unit-wise when we're talking about gas laws, and one of the big ones is the ideal gas law constant, R from PV equals nRT. And we are going to walk through how you can derive these so you can go from one to the other. The IB book is going to give you the first one, the data book, 8.31 Newton meters per mole Kelvin. But another one that actually comes up, I think, almost more often that can be kind of helpful, but you'd have to memorize it or be able to derive it, is 8.31 kPa per kPa decimeter cubed or kPa liter. That negative shouldn't be there. This would be kPa decimeter cubed per mole Kelvin. Let's see if it's fixed over here. Yes. So this would be correct here. Now the book gives you the 8.31 Newton meters, but a lot of times the pressure will be given in pascals, and so it's really easy to get it into kPa. And then sometimes the volume will be in meters, which we can then convert to decimeters cubed, and that's going to allow us to use this R in red. We are going to walk through how to also be able to use the R in blue, because that's the one that's given in the test booklet. Always make sure your N is moles and your temperature is always measured in Kelvin. Still need to make sure we're always in Kelvin for gas laws. All right, so kind of watch out on our units there. All right, next thing I want to do is go through some other gas laws like Boyle's, Charles, Gay-Lussac's, and kind of talk not only about what the relationship is. Where honors, we focus mostly on like memorizing almost what is the relationship and what is the formula, how to calculate that out. For IB, we also want to focus on why is that relationship the way that it is? Can you explain what pressure does to change the volume or vice versa? So let's first look at Boyle's law in this way. And you may remember Boyle's law is an inverse relationship between pressure and volume. So the formula is not set up like a proportion. It's actually P1V1 equals P2V2. Now let's talk about why. So first, let's define pressure. Pressure is essentially a measure of the force that's hitting the walls of the container. Remember, you have elastic and inelastic collisions here. The elastic collisions are the ones that are the gas particles hitting themselves inside the container, and that has no effect on pressure. The only thing that affects pressure is collisions with the walls of the container. How much force we actually are accumulating on the outside wall area. And so that is dependent on the space, because if we shrink the space, comparing this picture to this picture where we've decreased the volume, well, these particles are going to be hitting the walls of the container much more often. And so the force on that outside wall is going to increase. And that's defined as pressure, the force on the outside wall there. So we're increasing those collisions with the wall of the container because of the smaller space. So we would measure a higher pressure. So an inverse relationship. Smaller volume, higher pressure. Now let's look at Gay-Lussac's law. So this was the one that related pressure and temperature as a direct proportion. And so the formula just simply shows like any other type of direct proportion. P1 over T1 equals P2 over T2 or vice versa, as long as you have it set up like a proportion. Now let's talk about why. Why is it that an increase in temperature would lead to an increase in pressure? So this goes back to one of the main postulates of kinetic molecular theory. According to KMT, if we increase the temperature, adding that extra heat energy, that's going to be converted into a higher kinetic energy. And then you may remember kinetic energy is equal to 1/2 mass times velocity squared. So if I have a higher kinetic energy, literally moving much faster. So that velocity increase is very dramatic. Now, if particles are moving around way, way faster, they're going to be hitting the walls of the container much more often and with much more force. And so you're going to get more of that pushing on the walls of the container also defined as pressure. So if you have that increased temperature, that added energy into the system, you're going to get more of those collisions and measure a higher pressure. So pressure and temperature directly related. Gay-Lussac's law. All right, last one of our main three, Charles' law. So Charles' law was about volume and temperature. And yes, they are directly related, just like with the last one. So you're going to have any kind of proportion that'll work with volume and temperature. Now let's talk about why. Why does an increase in volume or an increase in temperature lead to an increase in volume? So first, as I increase the temperature, again, kind of starting with the idea of kinetic molecular theory, that increased temperature leads to increased kinetic energy, increased particle motion, right? So our particles are moving faster. Now, if the volume's not fixed, if it's allowed to move, that pushing, instead of just creating more pressure in a fixed volume, can actually push the walls outward. So if the volume is allowed to expand, then you have less volume. That increased movement caused an increase in the space that was being occupied. And that is going to allow the pressure to remain constant. Because now the collisions are more spread out over greater surface area, the total pressure that we're experiencing, that total force, is going to stay the same. So this is just showing the relationship between temperature and the pushing on the walls of the container. If we cool them down, they would start moving less quickly. There would be less force pushing that up, and so then the volume would shrink. So you get, again, that direct relationship where if you slow it down, now we take up less volume. More volume, moving faster, because they're moving faster. So that's our main three gas laws: Boyle's law, Charles' law, and Gay-Lussac's, looking at the relationship kind of one by one of pressure, volume, and temperature. Now let's move on to one that had only to do with the pressure, and that would be Dalton's law. So Dalton's law talked about partial pressure, meaning the pressures of individual components would add up to the total pressure. So it's a fairly straightforward law. If I had a balloon where I had 1 atmosphere of helium and 2 atmospheres of neon, the total pressure would be 3 atmospheres. Very straightforward. But it can get a little muddy when you actually go to apply it to an experiment. So probably the most common experiment where this comes up is when you're using a eudiometer in order to determine the volume of gas collected. So we actually did this experiment in honors where you put the magnesium strip, reacted it with the hydrochloric acid, single replacement reaction producing hydrogen gas. And so that hydrogen gas was collected in the top of that eudiometer. But because there's water there, there's also water vapor in that same chamber. So the total pressure would be the pressure of the hydrogen gas and the pressure of the water. And so if we wanted to isolate the pressure of the hydrogen gas, you would have to take your total pressure and subtract out the water pressure. So that's essentially what we do experimentally to isolate the hydrogen gas, or whatever gas it is that we're collecting. In a minute, we'll do one with, we're collecting carbon dioxide. So in order to isolate that, you take your given atmospheric pressure, you subtract out that water pressure. That's going to mitigate that problem of having the water when you collect over water, having the water vapor in the air when you collect over liquid water. All right, so that's Dalton's law. Partial pressures add up to a total pressure. All right, so now here's the experiment I was talking about where we're going to collect some carbon dioxide. And yes, we are going to collect it over water, so we'll be applying Dalton's law. In this experiment, we're going to be trying to find the molar mass. So let's think for a second what molar mass is all about. So molar mass, or relative atomic mass, M sub R, is always grams per mole. Now it's going to be heated up, and the best way I can explain this is to compare it to the hydrate lab. Originally, we have copper carbonate, just like originally you have a hydrated substance. Then in the end, we are evolving gas. Gas is evolved. And that gas that's evolved is called carbon dioxide, so CO2. It doesn't matter what the rest of the reaction is. All that matters is that this is the only gas. Whatever else is going to be evolved is still a solid. And I can tell that because it says we would still have that substance. A known mass is heated, the gas is evolved, and then we're collecting data. And the data table, I guess, would help to explain this part too. It has the mass of the tube that has the copper carbonate. And then after it's heated, they're still calling it copper carbonate here. Whatever is left of the copper carbonate, whatever that byproduct is, has this mass here, the 33.82. So it gave me an initial and a final, and the mass lost must be the mass of carbon dioxide. Just like when you start off where you mass the hydrate, then you dehydrate it, mass your anhydrate, and the mass lost must be water. In this case, the mass lost is our carbon dioxide. So if I find that difference, I'm going to be able to find the mass of my carbon dioxide. So that's problem number 1 handled. Now for the moles, that's a little bit of a longer story. How are we going to determine moles? What formula do we know that has moles in it that may also have volume, temperature, pressure? This is sounding like ideal gas law. PV equals nRT. The thing we want to be careful of is what units we choose as we go through these variables, because we're going to use an R that makes sense to our values. Now I have centimeters cubed, which I could easily convert to decimeters cubed. I have Celsius, which I'm going to need to convert to Kelvin. And the thing that I usually use to determine the best R is really the pressure. So in this case, it's giving me kPa. So the best R I would pick is 8.31 kPa decimeter cubed, or liter, over mole Kelvin. And so because of that definition, because of that R that I'm going to use, that's going to drive the conversion of all these other units. So let me go ahead and make a list here as I convert. So first let's do the volume. Volume given was 38.1 centimeters cubed. And I want to convert that to decimeters cubed. So centimeters cubed on the top, centimeters cubed on the bottom, decimeters cubed on the top. And this is just like liter and milliliter. So it's like 1,000 milliliters per liter, or 1,000 centimeters cubed per decimeter cubed. All right, so essentially I'm moving my decimal back 3 places. 0.0381 decimeters cubed. Now let's do the temperature. Temperature is 20.0 degrees Celsius, and to convert Celsius to Kelvin, we just add 273, which is going to make this 293 Kelvin, going with 1's place in terms of significant figures. Now pressure is a little tricky because they gave us 2 pressures. Why would they do that? There's an atmospheric pressure, and then there's a water vapor pressure. Well, anytime they're giving you the water vapor pressure, it's probably there for a reason. And if we go back and read carefully, you can see that this experiment is done by collecting over water, which means I have to take my atmospheric pressure and subtract out the water pressure in order to get the pressure of the actual gas, the carbon dioxide. So the pressure of the CO2 is actually the atmospheric pressure minus the water vapor pressure. So the atmospheric pressure was 103.6, and I'm going to subtract, kPa, and I'm going to subtract 2.3 kPa. And be careful too, you do want to make sure these are in the same units. They did give it to us in the same units this time. So I'm just going to do 103.6 minus 2.3. And I get 101.3 kPa. So now I have pressure, temperature, and volume all converted to the same units with R. So now I'm ready, I've got 4 of my 5 variables. I'm ready to plug it into the ideal gas law. So the pressure, so we're using PV equals nRT. The pressure is 101.3 kPa. Plugging in pressure first. The volume is 0.0381 decimeters cubed. I'm afraid I'm going to run out of room. Here, let's do this. I'm going to do N, and then I would plug in this R right here. And then the temperature was 293. Okay. So now to isolate N, I'm going to take 101.3 times my 0.0381, divide by R, and divide by 293. And I should be able to get the number of moles. So 101.3 times 0.0381 divided by 8.31, enter, divided by 293, enter. And I get 0.001585133. Now let's do scientific notation and 3 significant figures. So 1.59 times 10 to the negative third moles. Now that I have moles, I can find my relative atomic mass. So that's going to go in the bottom. And although I figured out what to do on the top, I never actually did it. So let's go ahead and subtract 33.91 minus the 33.82 here so that we can use that to get the mass. So 33.91 minus 33.822. And we get, to get MR as grams per mole, the grams on top are going to be 0.088 grams. Now, because we did subtraction, we're going to go with decimal places. So the 3 decimal places is our cutoff, exactly what it gave us. And that's going to now limit my relative atomic mass to 2 significant figures. I'm going to go ahead and divide by the moles that we have just up here, 1.59 times 10 to the negative third, and see what we get. 0.8 divided by 0.00159, and I get 2 significant figures is going to round up to 56 gram, and then I'll use the negative 1 on the mole there at the end. 56 grams per mole. Awesome. So this was a big one, big question. To start off with, you got to think about what our end game is. We need the relative atomic mass, or MR. So that's grams per mole. We can use mass loss concept here to get my grams of carbon dioxide, but to get moles, we have to go through the ideal gas law. And there's a lot of hiccups along the way with that, because you've got to watch your units. First, pick your R based on your units for pressure, and then convert the other units to match that R that you picked. So we had to convert to decimeters cubed, and you're always gonna have to convert to Kelvin, so, but yes, that is part of R as well. And then with pressure, you gotta watch out for, if you collected by displacement of water, which is a very common experimental technique to use, then you always have to subtract out the pressure of the water vapor before you actually use that in the ideal gas law. Once we get that all figured out, now it's just the algebra to get to moles. And I know that was a lot of work, but don't stop there, because you still have to convert, or use it to calculate, I should say, not convert, your grams per mole. So using your mass loss and dividing it by the moles that you got from your ideal gas law. And then you can finally get your answer of 56 grams per mole. All right. Okay, moving on. Slowly but surely. Here we go. One last thing that I want to talk about with ideal gases, and that is what actually makes it act like an ideal gas. What does it actually mean to be an ideal gas? So the main idea behind an ideal gas is that it has absolutely no intermolecular forces. In theory, there is 0 attractive force from one particle to the other. And this can actually be analyzed experimentally. If we look at how the number of moles change over pressure, and you might identify this as like a manipulation of ideal gas law. PV equals nRT. And if you isolate moles by dividing by RT, that's where we're at here. So this is a fancy way of saying, looking at moles as it changes per pressure, an ideal gas should be a constant flat line. So that ratio should stay the same. But when you look at real gases, you're going to see what we call deviations from the ideal gases. Things that do not behave this exact same way. And if we look at what type of things fluctuate the most, we can determine what conditions are best for ideal gases. And that turns out to be low pressure, high temperature. So first let's look at the pressure. And so as your pressure is increasing as you're going from left to right here, you see in the beginning, looking at the purple line would probably be the easiest, the pressure isn't changing it much from the way that we would expect it to behave. But then as you go further to the right, you're getting a bigger and bigger difference in the behavior that we would expect. So as we increase the pressure, we're getting a bigger deviation from the ideal gas law. Now with temperature, you have to compare this line for a few different temperatures. So we see here 200K, 500K, 1000K. So the hotter one is flattening out closer to the ideal gas law, whereas the cooler it gets, the more it's fluctuating away from what we would expect an ideal gas to do. So the higher temperatures are making it act more like an ideal gas. Low pressure, high temperature. Now I wonder why that is. So let's think about each of these one at a time. So first, pressure. Why do we think that increasing the pressure would actually make it act more like or less like an ideal gas? Well, think about what increasing the pressure does to the spacing between the particles. If I have a low pressure, those gases are more spread out. If I increase the pressure, I'm forcing those particles to get closer together. So if I have a higher pressure, there is much less space in between the particles. Now, particle spacing is a big factor on the strength of the intermolecular attractions. That's why solids have the strongest intermolecular attractions, weaker for liquids, and then theoretically none for gases, right? So if we're pushing those particles closer together, we're forcing them to interact with each other. Those interparticle or intermolecular forces, attractions, those become stronger when those particles are closer together. So how do I mitigate that? Lower the pressure and let those particles get as far apart as possible, and so that way they're not going to be feeling each other's forces as much. So gases are more ideal at a lower pressure. Now what about with the temperature? Keep in mind kinetic molecular theory. If I have a lower temperature, the particle would be moving slower, allowing those particles as they're moving slower to feel each other as they pass each other. Now if they're moving so fast, they're not in each other's space for very long. So those fast moving particles are not going to feel as much of those intermolecular forces. So the gases will act more ideal at higher temperature. Low pressure, high temperature is going to minimize the intermolecular forces. An ideal gas would have 0 intermolecular forces. All right, guys, that's going to do it for our gas laws notes. Our next notes will be a review for the test. So we'll see you there.